Hey guys, this is Gargi and you are watching The Dazzling Dentist. So in today's video, we are going to discuss about the methods of strengthening ceramics. So the strengthening of ceramics can be accomplished by either of the two methods. First is development of residual compressive stresses within the surface of the material, and second is interruption of crack propagation through the material. Now, under the first one, we have development of residual compressive stresses. So, the main principle is to select a core material that contracts slightly more than the veneering ceramic when cooled to room temperature. On cooling from the firing temperature to room temperature, the inner metal core contracts slightly more than the outer ceramic layer. And this variation will cause the metal to pull the ceramic inward, resulting in its compression and thereby inducing residual compressive stresses within the ceramic. The same principle applies to the metal-free ceramic materials also, where the core ceramic has a coefficient of thermal expansion slightly higher than that of the veneering ceramic. Now let me make this clear through an example. Now let us suppose that the white part is the ceramic and the underlying blue part is the metal core. So after firing, when the restoration is cooled down to the room temperature, the inner metal core will contract slightly more than the ceramic because of high coefficient of thermal expansion, and it will pull the ceramic inward, which will result in its compression and thereby reducing residual compressive stresses in the ceramic and hence will lead to strengthening of the ceramic. Now second is reduced number of firing cycles. So during the firing cycles, several chemical reactions take place of which increase in concentration of crystalline lucite occurs. Lucite, a high expansion crystal phase, greatly affects the coefficient of thermal contraction of porcelain. Multiple firings increase the thermal expansion coefficient. So when this expansion coefficient exceeds that of metal, the mismatch between the porcelain and the metal will result in stresses during cooling that induce crack formation and propagation. Basically, during the firing cycles, several chemical reactions take place which lead to increase in concentration of lucite. And lucite affects the coefficient of thermal contraction of porcelain. So if there are increased number of firing cycles, there will be increased thermal expansion coefficient. And so when there is mismatch between the coefficients of thermal expansion of porcelain and metal, it will ultimately lead to crack formation and propagation. And this can be prevented by minimizing the number of firing cycles, thereby controlling the formation of crystalline lucite. Now next is optimal design of prosthesis. Tougher and stronger ceramics can sustain higher tensile stresses before cracks develop. So, the ceramics should be tougher and stronger. Sharp line angles and abrupt changes in the contour in the preparation of all ceramic crowns result in areas of stress razors in the ceramic. Line angles should be well rounded for all ceramic restorations. Another way of reducing tensile stress is to provide adequate thickness on the occlusal surface of a minimum of 2 mm. Now the tensile stresses in a ceramic fixed partial denture can be reduced in two ways. A. The height of the connector can be increased to a maximum of 4 mm, and B. The radius of curvature of the gingival embrasure portion of the interproximal connector is broadened. Now the fourth method is ion exchange. So, when sodium containing glass is immersed in a molten potassium salt, the potassium ions present in the bath exchange places with the sodium ions present on the surface of the glass and remain in the place even after cooling. This is a concentration driven effect and an equilibrium will eventually be established, not a complete exchange. Since the potassium ion is 35% larger than the sodium ion, the potassium ion will have to squeeze into the place of sodium ions, creating large residual compressive stresses. And this process is also known as chemical tempering. Now just suppose that the sodium containing glass is present in molten potassium bath. So the sodium ions are smaller than the potassium ions and they will ultimately get exchanged with the potassium ions, and the potassium ions have to squeeze in the place of the sodium ion and it will lead to residual compressive stress. Now the fifth is thermal tempering. So the rapid cooling of the surface of material while it is still in its molten state by quenching forms a rigid surface with a still molten core. As the molten core starts to solidify, it starts to shrink and it pulls the rigid outer surface inwards. This results in residual tensile stresses in the inner core and residual compressive stresses with the outer surface, which is rigid. This is the most widely used method to strengthen glass, and in dentistry, silicone oil or special liquids are used to quench ceramics instead of water or oil. So when there is rapid cooling of the surface of a material by quenching with silicone oil or special liquids, the inner core still remains molten while the outer surface gets solidified. So as the molten core starts to solidify, it starts to shrink and it will pull the outer solidified surface inwards. And this will result in production of residual tensile stress in the inner core and residual compressive stress within the outer surface, and ultimately lead to strengthening of glass. So a fundamentally different method of strengthening glasses and ceramics is to prevent or stop crack propagation, and this can be done by the following methods. First is dispersion strengthening. So ceramics can be reinforced with a dispersed phase of a different material, and this dispersed phase will interfere with crack propagation through the ceramic material. This can be accomplished by the addition of tougher filler particles which absorb the energy from the crack and prevent its driving force of propagation. So, when a tough crystalline material is added to the ceramic, cracks formed in the matrix cannot propagate when they come in contact with the tough crystal particles. These crystals act as roadblocks to the spreading of the crack. The crack has to go through or around a crystal. This results in diversion of the energy from the crack propagation or stopping of the process completely. So just suppose that there is addition of a crystalline phase in the ceramic. So when there is initiation of a crack, it will get blocked by the crystalline material and it will stop the spreading of the crack, leading to strengthening of ceramics. Next is transformation toughening. The other method is to bring about a change in the crystal structure under stress, which absorbs the energy required for propagation of the crack. Example: dental ceramics containing zirconia crystals namely partially stabilized zirconia. Zirconium oxide, when heated to temperature above 1470 degrees Celsius, undergoes a change in its crystal structure from a tetragonal to monoclinic phase. As the controlled transformation from metastable tetragonal phase to stable monoclinic phase occurs, it results in crack shielding and toughening of the ceramic. Now just suppose that these are tetragonal zirconia crystals present in the ceramic. When there is propagation of crack, the zirconia crystals that are tetragonal will get transformed to monoclinic form. And this will ultimately lead to strengthening of ceramics. So that's all for this video. Don't forget to subscribe, like, share and comment below. Thank you.